Hi, Joe Cerrone.
And Al Rosen.
Welcome to CAD 107. So as we take a look at our main splash page, we've released Lab 9, which is the napkin holder. And this project is going to be designed using AutoCAD. We look at Module 9 under our content section. In Module 9, we'll be covering the Chapter 8 of the textbook. And I'm going to just go ahead and download that and launch it. And so I've already downloaded it. I'm going to open that here. And we're going to talk about Chapter 8, Design Rules for 3D Printing. And so as we start to work with our CAD in our slicer, there are certain design rules that we want to work with. So as we progress through the course, we've been creating these different CAD models. And so here's an example of some of the CAD models. Last week, we worked on our pencil holder. And so we have that modeled here, and we can take a look at that. As we take a look at some of these different prints, so here's an example of how this would come out on our 3D print. It takes about 5 hours to create the geometry for that, or to print that. And then if we wanted to print this, we remove that from the build plate with our and we can see that it's a decent build. Notice that we have a logo here, so we can identify whose part that is. That's very important. And then you can see that as we take a look at this, this part came out just fine. It will hold our parts. Everything is designed so that it all holds together. Pieces aren't independent or falling apart. And so this is a good print. We take another print. And this one's just sliding right off the build plate. I don't even need to remove it. And so you can see that we have used a brim on this, and that's to keep it from peeling, because what will happen on some of them, here's a failed print. And what happened was the build plate, or the part, actually shifted on the plate and then came off, and then it would create this big glob of printed material because the part is shifting around as it prints. And so it's very important as we start to design for 3D printing to work with our build plate adhesion. Okay, here's another example. We can take that part off. Notice again too that we want to have some kind of identifying marks on the print, because some of them will look quite similar. And so we have someone who has engraved their name. And as we talk about engraving and things like that, there's a difference too between engraving something in AutoCAD, like this print right here, which was done with text, versus 3D. But we definitely want to make sure that we put some identifying features onto the print. So as we look at our design rules for 3D printing, we've created these CAD models, and then we export them as an STL and then we bring them into the slicer. And when we bring them into the slicer, the orientation of the part is important. So for example, if we're looking at opening a part here, what we want to do is we want to orientate it onto the part, onto the build plate. And so if we move this onto the build plate, you can see that this is not properly orientated. Will it print this way? Yes, it will. If we prepare it, it will go through and slice it. And then we can view these different layers. But essentially, this would be a failed print because it doesn't have any build plate support. And so orientation is very important and time is important. So this is this is about a 12-hour print. When we generate support for it, and this is on low quality with PLA, now that we have generated support, we've increased the build time to 16 and a half hours. And we can look at that, but this is an example of how we can orientate this by rotating it 90 degrees and then reslicing it. And it's really not going to need that much support, even though we have generate support enabled. It doesn't really need any. And you can see it doesn't generate any support. And it also cuts down about 6 hours from our build time. So the orientation of the part in the 3D slicers is very important. Continuing. So we're going to talk about FDM printing, filament deposit modeling. Here's some examples that we had just talked about. When we're working with filament-based printers, we want to make sure that the build plate and the part are anchored solidly to the bed. That seems to be our biggest problem. When we don't apply glue or adhesive and the part comes off the build plate, it will fail.
Hey, Joe,
Mm-hmm.
it says brim. Is there another way besides a brim that shows at that picture right down the bottom?
Yeah, if we wanted to look at some of the different examples, okay, and so let's disable our support here. I will put a skirt on because it will prime the nozzle for the first layer. And the first layer is the most important because that's what sticks to the build plate. But what we will find is that we can use something like a raft instead of a brim, and that will give it an even more firm grip. Now I have to bring it down a little bit because the raft is too big, the number of margins. So let me bring this down. Let's bring it down to 7. See if it will prepare it now. It will not slice it if it will not fit within the printable area. And so within the printable area here. And so, yes, we can print this with a raft and that will hold it down even more securely.
Okay.
All right, continuing. So when we work with filament-based printing, we want to make sure that we adhere the part to the build plate. Another thing that we want to look at is what kind of angles we can print with. In other words, how much overhang before the part will start to fail. And so if you go on Thingiverse and take a look, they have all of these models that you can print out to test your 3D printer. And so we can go and we can take a look at that, and we can go to Thingiverse. And we can download and print this overhang test. And so I'm printing one right now. If I switch cameras, this is an example of printing with an overhang. And as you can see, it's able to print and we can analyze the overhang test. And so we're able to print this, but you can see it's starting to get a little bit where it's just starting to, this is a better angle of it. It's just starting to fail. In other words, the overhang is just a little bit too much as it gets to the 75-degree angle mark. And so we have 15 degrees, 30 degrees, 45 degrees, 60 degrees, and then 75. And then we can bring this up and over all the way up to 90 degrees to see how our 3D printer will print. And then there's some other examples here too, as far as to be able to see how our bridging is working. And so as we go through and we start to work with the capabilities of our 3D printer and designing for 3D printing, we want to check our capabilities by running a 3D printer test and then being able to analyze that. So back to our PowerPoint. So as we're working with our 3D printing and designing for 3D printing, we want to be able to consider how much overhang our designs can work with without printer support. Now, we could certainly bring this into the slicer. And what I've done is I've got it on my computer here. We can just click it and drag it into the build plate. And then we can analyze our print and the overhang. And so as we look at this, we can see that we can print up to, and I stand corrected, I think I said 90 degrees, but it's 80 degrees. And that's just the lighting in the room here. 80 degrees is about the maximum before it starts to fail. And then as we look at some of these other aspects where we can go through and look at our print, We can look at things like scale tests, stringing tests, diameters, and then we want to gauge those. And so we want to use our caliper to be able to check the accuracy of those prints. Another test is the bridging so that we can see, and that one had bridging built in, but there are other bridging tests. And so if we were to look at this print right here, this is a test which will allow us to see the maximum amount of bridging, and this will be our next test. And you can also see that they're also going through and seeing what the maximum amount of overhang. Another test that we can run is some of these other print tests where we can go through and print things, check whether they need support or infill percentage, and we can go and check that as well. And so in these prints, we can go and see what the shell thicknesses can be, our infill percentages, and our supports. And we'll print those and leave those in the lab so students can get an idea of what the capability of our printers are. In our models, we can go ahead and kind of analyze the infill and things like that. And so if we want to take a quick review of some of our projects, we can take a look at those. And so if we take a look at this print right here, this is a print that we're using for our CAD 118 course. You can see that we've used build plate adhesion to make sure that the parts stay on the build plate. And that's because they're round. You know, as we look at these cylindrical shapes here, we would have very little contact with the build plate, and the chances of it coming off would be considerable. And so we want to use build plate adhesion for things like this. Sometimes when we print cylindrical objects like this, they'll come out a little bit elliptical. And so we want to pay attention to the orientation for that. And then we can take these parts off. And then we can check to see if they fit. And so we'll remove the material. And this is a good example of why we want to have some additional processing tools. You can see that there's some support material on here as well. And so we want to pull that off. And then we want to have a set of files that we can use to be able to post-process these. And so these are just some Harbor Freight files that we can go through and we can use to remove some of the material and do some post-processing. And we can see that this part is just going to need to be toleranced or filed quite a bit more before it's able to actually fit. Now, one good thing is that we can always open up these holes a little bit more. And so sometimes we can go through and we can drill these out. It's almost the right size. I think with a little bit of sanding, I could get this to fit and to get that to work. But ideally, I would probably take off about a 32nd of an inch when I created the design for the cylinder so that it would fit better. And so those are some of the things that we're working with as we go through and we work with 3D printing and designing for 3D printing. Tolerances, being able to have the parts fit together. So as we progress, our next design will be this napkin holder. And in the napkin holder, we have two versions of it. And so we have this version, which has inserts, which you can print. And again, we're going to want to make these about a 32nd of an inch smaller than the other side of the design so that they fit together so that you can place them like a jigsaw puzzle. The other print that I had designed was to have the logo is just being removed. This part takes a long time to remove the support material in the post-processing. So this part is actually quicker and more reliable than this design right here, because this design requires a considerable amount of post-processing. And depending on the type of printer you have, if you have a single extruder printer, then you'll have to chip that away. But if you use a water-soluble support, then you can put that into an immersion tank and you can remove the material that way. If we look at the designs for our lab number 9, we can go. So when we look at lab number 9 and we're working on this napkin holder, we have a couple of different designs. This was the original design from the textbook. And so if we look at that, and you're welcome to use whatever CAD program you're most familiar with, but we teach the course with AutoCAD. We can do SolidWorks as well, and some people are using Fusion. But as we look at this, what we're going to do is we're going to design this using metric units. It's 157 millimeters by 94 millimeters. And I'd say this is probably the most critical area where we'll see that we need to have the part adhered to the base. And so it's got this triangular, actually rectangular, square shape on the bottom that we can go through and we can design and build. And if we look at the part that's been created in AutoCAD, this is the version that doesn't use an insert. And so this would be created. And what we've done is we've outlined it like we've done in other modules, where we'll start off with the original CAD geometry. And if we take this in the top view, and we analyze it, we can click on that, hover over one of the grips, and we can see that it's 157 millimeters. And then we basically create the part according to the geometry, and then we extrude it with a thickness. And if we want to analyze the thickness on that, we can measure the distance. And we can see that it's 3 millimeters. And so we extrude those 3 different components. We rotate them. We union them. And then what I did was I created a logo of the oak leaf, which I then extruded and subtracted. And so here we have our component, and then we can export that as an STL file. And so I'm going to export that to my downloads. And I'll hit save. I'll select the part. I'll hit enter. And then I'll go into my slicer and we'll start a new file. And then we can open that from our downloads. And again, we want to orientate it properly. And the other thing I want students to do is to put their name on it. And you can either use CAD to do that, or we can use 3D Builder. I'm going to use 3D Builder for this.
Hey, Joe.
Mm-hmm.
When you're going to put your information on it, would it be easy to do it as it is a full one object, or before you put it together? What do you think?
I would do it as a full object after it's been created.
Oh, okay, good, thank you.
So we'll open the object file from my downloads. Comes in millimeters. We'll recognize it and check that off. And then what we can do, a lot of times I will orientate this to the 0 position. And so I like to tie machine 0 or 3D printer 0 and my part together. And then what I'll do is I will edit it and emboss it. And so we want to put our name on it. And so I'm just going to use Oakton College. You can add colors to the top and to the sides if you want. And so if I wanted the top to be a light so we can move that text down and emboss it, and then we'll check mark that. And then if we want to put another one on the other side, we can flip it around to the other side and we can go to emboss again. We want to save it as an STL file. And I'll just save it to my downloads again. I'll add an X to it. And I'm going to make that STL file format. And we'll save it. And it prefers the 3MF format. Come into our slicer. We'll take out the one that doesn't have the embossed image on it. We'll open up the one that does. And then we'll prepare it. And you can see we have support generated. And what it will do is it will generate the support in the inside area. And this takes a bit of work to remove. And so we could also work with our version 3, where we can go through and bring in a part that we can then go through and add inserts to. And so if we take a look at that, here is our object. And let's just verify that with a conceptual. And we can see that this component is not all the way through. And this should be a faster build time. And so this is 4 hours and 4 minutes. I'm not sure if it'll be faster, but let's find out. And so we'll remove that, come back to our other component, and we'll export that out. We'll save it, hit enter. And then we'll export out the logo as well, because we're going to be putting that in, and we'll print that on a separate printer with a different color. And then I'm going to export the holder again because I don't think that went into the right spot. We can go into our slicer and then we can open those. And again, we're going to need to orientate that. And so we're going to rotate that about the z-axis, the x-axis. And then we can slice that. It's about the same, 4 hours and 4 minutes. We remove the support and reslice that. We can see that we have the part on the build plate. Just from a standpoint of being able to print the other component, I'm going to open that up. And what we can do is we can print that. We could print two. We could print these in silver and then print another one in green. And then we can swap the image of the logo and insert that into the part. We prepare that. We can see that we can print this in 3 hours and 52 minutes. So it is a quicker build time as we go through and we work with designing for 3D printing. All right. So as we continue working on this project, we're going to work on lab number 9. Remember, you're welcome to come into the class if you would like to work in person as we do our broadcast from the Skokie campus in room P130. With that, I'm going to stop the recording and open things up for questions.